Hello. In this video, we're going to work through the January 2026 exam. Now, before we get started with the actual exam, I want to go through some of the introductory pages. Here we can see our formula sheet, and this is the one we've been using throughout the course. It has formulas like the arc length, our trig identities, our log laws, permutations, combinations, etc. And so you'll tear this out and use it as you go through the exam. And if there's anything you wanted to write on here, you're more than welcome to mark it up, maybe make a quick reminder. It might be helpful, for example, here for arc length to put a quick reminder that theta has to be measured in radians, little things like that. The next page is our terminology sheet. This is also important because we're going to see words like describe or determine, and we want to make sure we're answering the questions properly. So for example, if you see the word describe, that means you have to use words. So it's very important that you don't just put equations, you also include some English to describe what's happening. Whereas if you see the word evaluate, that just means you need to find the final numerical answer. And of course, it's good to box your final answer. Again, look at the word explain. It says use words to provide the cause or reason. Even if you look at a term like, let's say, justify, we have to show reasons for justify. And showing reasons could look like some math, but it also could include words. Because if you look, we use mathematical computations and words and or diagrams. So we want to make sure that we're reading the questions properly and using words when needed, numbers when needed, even something like as simple as verify. That means that you're not solving, but you're substituting or comparing. We've been over many of these terms in class before, but it's just good to keep this vocabulary sheet handy as you're going through the exam. And if you see a word, you maybe forget what it means, justify or verify, explain, evaluate, you can come back and refer to this page. Now we've also got our unit circle here, and I always recommend that students make at least the first quadrant. So we want to add our points 1, 0, root 3 over 2, 1/2, root 2 over 2, root 2 over 2, 1/2 root 3 over 2, and then 0, 1. If you want, you can also add the cast rule here. So we have CAST. We could also put the tan values next to these. So tan here will be 0, 1 over root 3, 1 root 3, and then undefined. We could mention that the x, y is going to be cos theta, sine theta. We could mention that tan is equal to sine over cos. And if we want, we could include some radians as well. So 0, pi over 6, pi over 4, pi over 3, and pi over 2. Now you might want to put all the radian measures around the inside, but in terms of the actual coordinate points, we can figure out the other ones by just mirroring them over. So for example, if we needed to find maybe this one over here, we would take this one and we would mirror it this way and then this way. So that would make both of the coordinates negative. So if we were asked to find this value over here, it'd be negative root 2 over 2, negative root 2 over 2. Remember, we don't want to make a nice pretty unit circle and spend 10 minutes on this page. It says right at the top that no marks will be awarded for work done on this page. This is simply a reference for yourself. So add that first quadrant, maybe add a few more radians if you need to, and then go ahead and continue on with the exam. All right, here we go. Question 1. Liam went for a ride on a Ferris wheel with a radius of 5 meters. Determine the distance he traveled if the Ferris wheel stopped after rotating 1,260 degrees. So we've got 5 meters and we've got an angle. Remember that when we're doing these questions, we see very clearly at the top, there's the calculator icon here. So anytime we've got that calculator icon, it means we're expected to use our calculator. We're going to need it on these questions. And that's because our radian measurement here is not actually in radians, it's in degrees. Theta needs to be in rad, so we can take that degree, multiply by pi, and divide by 180. And that's going to convert it into radians. Now that's going to be a nice number. That's going to be 7 pi, and we can leave it exact. Next, we're going to use our arc length formula, S equals theta r. So we're going to get 7 pi times 5, so 35 pi. And then we want to include the units, so meters, or you could just write m for short. Now, if you wanted to write it as an exact value, this is perfect, but if you wanted it rounded with some decimals, you could also write it as 109.956 meters, and that would be acceptable. Just remember that you're going to 3 decimal places, because if you're going to round it, you have to go 3 decimal places at the final step of rounding. Make sure you include the units, and make sure you box your answer. Question 2, determine and simplify the term that contains x to the 12 in the binomial expansion of this. Well, we don't know the term, so we have to determine the term. We're probably going to need that term formula, right? Tk plus 1 is going to be nck. 2x to the 4 to the n minus k minus 3 to the k. Now there are a few things we know here. This 7 is going to be our n. So we could put that in here. There's a 7 there. There's a 7 there. And the key thing is we're trying to get an x to the 12 out of this term right here. So whether you do it by pattern recognition or setting it up, we have to figure out which term is going to have that power of 12 in the end. So let's go ahead and do the method where we determine the pattern. So if you think about the binomial expansion, the first term is going to have 2x to the 4 to the 7. And then we're also going to have a minus 3 to the 0. And then we'll have a Pascal term as well. But none of those are going to add x's. So we're just going to focus on the 2x to the 4. Then we'll have 2x to the 4 to the 6, 2x to the 4 to the 5, 2x to the 4 to the 3, 2x to the 4 to the 2, and so on. And if we look at each one of these, we can imagine what the x is going to become. Here we have 4 times 7, so that's going to be 28. We'll get x to the 28. That's going to be x to the 4 times 6, so 24. X to the 4 times 5, so that'll be 20. And then we've got x to the, oh, it looks like I missed a term here. 2x to the 4 to the 4. That'll be x to the 16. 2x to the 4 to the 3, that'll be x to the 12. Oh, there we go. So this is going to be the term I need. And I can now count along 1, 2, 3, 4, 5. So this is going to be term 5, which means k is equal to 4. So now that I have my k and I've determined the term, I can go back to that term formula I was trying to work with. T4 plus 1 is equal to 7c4, 2x to the 4 to the 7 minus 4 minus 3 to the 4. Now we do have a calculator handy, so we can go ahead and calculate 7c4. That's going to be 35. 7 minus 4 is 3, so 2x to the 4 to the 3. Minus 3 to the 4 is going to be 81. Now we do have to just be careful here. Remember with this 3, it's going to power both the x and it's going to power the 2. So we're going to have a 2 to the 3. That's going to be 8. So we got a 35 here. We got an 8. Got an x to the 4 times 3, which is 12, and an 81. So let's take all those number portions and multiply them together. We're going to get 22,680 x to the 12. And that's our final answer. Question 3. We've got a word problem here. The normal healing of wounds can be modeled by an exponential function. The area of the wound decreases according to this formula. Okay, so we have some formula here. Then they're going to explain it to us. A equals something. A0 equals something. Time equals something. If the wound has an initial area of, okay, so there's some information. 25 centimeters squared, determine the area of the wound after part A, 3 days. So the initial area, we're told that's right here. So this is our A0. 3 days, time is in days, so this is going to be our T. So we should be able to set up the formula A equals 25 e to the minus 0.35 times 3. And that looks like just a calculator question. So we should get a value of 8.748. The next number is a 4, so it rounds down. Centimeters squared. Because it says here A is measured in centimeters squared, so let's include the units. Box it up, and we're good. Now let's check out part B. Part B says the amount of time it will take for the area of the wound to decrease to 4 centimeters squared. Okay, so this, we're now looking for time, and we're told it's supposed to be 4 centimeters squared. So we're looking for time. Time is going to be our unknown. This is going to be our A. And we still know that the initial area was 25. So from before, we know that A0 is still 25. So let's see what we get in our setup. 4 equals 25, e to the negative 0.35 t. Okay, so this is now an exponential equation, so I have to solve this. The first thing I'm going to do is divide both sides by 25. Now 4 over 25, that'll be a nice decimal, so we could write that as 0.16. If it was not a nice decimal, I might want to leave it on my calculator or leave it as a fraction. But if it's just a simple decimal that terminates, we can put that in as a decimal. Now we're going to go ahead and take log of both sides. In particular, we'll take ln of both sides, the natural log. So ln of 0.16, I don't want to type that on my calculator because I know it'll be too many decimals and I need the exact value. Here we can bring down the negative 0.35t using our log laws. And of course, ln of e, that's just going to equal 1, so I can put that in. So 0.16 equals negative 0.35t times 1, doesn't matter. Let's divide out the negative 0.35. And so now I type that in on my calculator. Let's take a look. ln 0.16 divided by negative 0.35, 5.2359. So let's make that a 6. And that'll be days, so we'll include the units, and we're good. Now, it doesn't say how long until it is decreased to at least this amount, or it doesn't say how many whole number days. So we can leave the days here as a decimal. We don't have to round it to a whole number. Question 4. During a hockey practice, 4 players are wearing a green jersey and 5 are wearing a red jersey. Determine the number of ways 3 players can be selected if at least 2 of the players must be wearing a red jersey. So we've got to look for that at least. That means we were going to do something with cases, I'm thinking here. And we've got some players, so we're thinking some kind of permutation or combination question. In particular, we don't have any names for the players, and they're all wearing sort of the same thing, just a generic jersey. So I'm thinking this is going to be a combination question. Let's think about the different cases we could have. Well, we're going to be selecting 3 players, and at least 2 of them have to have a red jersey. So we have the case with, let's say, 2 red, and we have the case with 3 red. Because 2 red is at least 2 red, and 3 red is at least 2 red. So how would I make 2 red jerseys? Well, I would take the 5 red that I have available, and I would choose 2 of them. And then I would still have to take the 4 green jerseys and choose 1 of them. Right? I'm going to need 2 red and 1 green to make the total of 3 players. Type that in on a calculator and we get 40. 3 red, well, that's going to be 5c3 times, you can put 4c0 if you want because there's 0 green, but this also can just be ignored because it just equals 1. It's up to you. That's going to multiply to 10. And then we always remember to add between the cases, so that's going to give us 50. So the answer is 50 ways, or there's 50 options. Here it says the number of ways. So you could write ways, but 50 is fine. Question 5. Notice we no longer have a calculator icon here. So we're actually done with our calculators. We don't need them for the rest of the exam. You're still welcome to use them on any of the questions in the first booklet during the first 45 minutes. And you might find a question or two where maybe it's easier with a calculator, or it might help you double check some mental math. But generally speaking, that means going forward, the numbers will be relatively small, and we won't need to do any large calculations because we won't have a calculator. So let's go ahead and solve algebraically over the interval 0 to 2 pi. Now, we've got ourselves sine and cos, and that's a bit of a problem. Whenever you have an algebraic equation with sine and cos, you can't solve it. You need to convert one into the other. So let's go ahead and convert that sine squared. Based on our formula sheet, remember that sine squared x plus cos squared x equals 1. In other words, sine squared x equals 1 minus cos squared x. And there's going to be a 2 in front of it, so we've got 2, 1 minus cos squared x plus 5 cos x plus 1 equals 0. Negative 2 cos squared x plus 2 plus 5 cos x plus 1. Then we can put that 2 and the 1 together, so negative 2 cos squared x plus 5 cos x plus 3. Now I don't like a leading negative, so I'm going to multiply the whole thing by minus 1. So I'm going to get 2 cos squared x minus 5 cos x minus 3 equals 0. Then we need to factor this down. And you can do this by doing a substitution. If you don't like seeing so many cosines everywhere, you could say let cos x equal y or something. You couldn't say x because there's already an x. But you could factor this as 2y squared minus 5y minus 3. If that made it easier to look at the factors. So we're looking for two numbers that multiply to give negative, well, 2 times 3 is 6. Two numbers that add to give negative 5. So I'm thinking negative 2, negative 3. No, that's not going to multiply to negative 6. Maybe 6 as a negative and 1 as a positive. Yeah, well, that will multiply and that will add. Sweet. So 2y squared minus 6y plus y minus 3. So 2y is going to be y minus 3 when we factor it out. Here we just have a 1 as our placeholder to factor out. So y minus 3, 2y plus 1 equals 0. And substituting it back in terms of cosines, well, I guess we could keep going here. This means y minus 3 equals 0, and it means 2y plus 1 equals 0. So y equals 3 and y equals negative 1/2. So now that we've fully solved it, we can put it back for cosines. This means cos x equals 3. And this means cos x equals negative 1/2. All right, so now we have to take these and we have to convert them into actual radian values because we need our stuff from the unit circle. Now we know that cos of x never equals 3 because the range of cosine is between minus 1 and 1. So underneath this portion, we're going to say no solution because cos x never equals 3. And since we do have our calculator handy, we could always check this, right? We would do cos inverse of 3. And as long as we're in radians, just to make sure we get the correct answers. But that's going to give us a math error or no solution. So that's how we know we get no answer. Over here again, because we're in the calculator section, we could do cos inverse of negative 1/2 on our calculator. And so if we do that in radians, it's going to give us 2 pi over 3. But using our calculator here, I don't really love it. It's going to give us values in weird quadrants. We're not going to have the reference angle. And so generally speaking, I think it's just a better idea to go ahead and use that unit circle. So if we grab that unit circle from the beginning, we're looking for cos to be negative 1/2. So cos is going to be 1/2 up here. And so we're looking for negative 1/2. Using that cast rule, it's going to be here and here. So there's going to be one value here and one value down here. This is going to be 2 pi over 3 like our calculator showed us. And the other one is 4 pi over 3. So we've got to circle up our two answers. We have our no solution. And we're good to go. Again, the interval was 0 to 2 pi. We weren't asked for the general solution or something like that. So this is sufficient. The function y equals fx has a domain -8 to 4. The domain of the graph y equals f bx is -4 to 2. State the value of b. Because we only have to state the value and it's a single mark question, we can just put the answer. So I'm going to put the answer equals 2. But you might ask, how did I come up with this answer? Well, let's go ahead and back it up a little bit. We know the initial domain is -8 to 4. And we're going to do a horizontal stretch. And we're going to get the domain to be -4 to 2. So it's almost like we had the graph. And it used to go from here to here, -8 to 4. And now it goes from here to here, -4 to 2. So it's been shrunk down. It's half as big. You can think of this point 8, it went to 4 because we divided by 2. But we don't like to think about dividing when we're doing transformations. We always want to think about multiplying. So we multiplied by a half. Now you might be tempted to say, oh, b's got to be a half. But remember, if we were to put f of 1/2 x, because the rule is that the horizontal transformations get flipped, the 1/2 actually would be a multiplication by 2. So to get the multiplication by a half, we have to flip that itself and put the number 2 in here. F of 2x means a horizontal stretch by a factor of 1/2. So that means the answer is b equals 2. Question 7. Describe the difference between the graph of this function and the graph of this function. Well, again, that's a 1-mark question, but we are looking for the word describe, so we're going to want some English. And these two factors cancel. That's the difference. So in the equation, you could say one of them has an uncanceled factor, but we're looking for the difference in the graph. So what does this canceled factor do to the graph? Well, for this function, it creates a hole at x equals -3. Or if you want, you could call it a point of discontinuity. And for this graph, we're going to have no hole. It's going to be just a regular linear graph. So the difference is that fx has a hole at x equals 3, gx has no hole. And that's a nice sentence that clarifies which graph I'm talking about, which one has the hole, and which one doesn't. Question 8. Determine if the point -3/5, 2/√3 is on the unit circle. Justify your answer. So we need to provide some justification. We can't just say yes or no. And what we're going to use is the equation for the unit circle. X squared plus y squared is supposed to equal 1. So let's go ahead and calculate x squared plus y squared. -3/5 squared, 2/√3 squared. It's going to give 9/25 plus 4/3. Now I need to make these common denominators, so think 75. So let's multiply by 3 here. Multiply by 25 over here. 27 plus 100 over 75. So that's going to give me 127 over 75. And that does not simplify to 1. This is not equal to 1. So not on the unit circle. Remember, there are points that could be on the unit circle that we haven't memorized. Just because it's not our root 2/2 business doesn't mean it's automatically disqualified. What disqualifies it is that it does not satisfy the unit circle equation. Question 9. Given the graph of fx, sketch the graph of gx equal to this equation. Well, let's unpack what each means. Here we have a horizontal reflection. Here we have a horizontal translation of 1 to the right. And here we have a vertical translation of 3 up. So what this means is that for our x and y, we're going to have to take the x values and multiply them by -1. So we're going to have to take those x and make them -x. And then we're going to have to add 1 to them. For the y, we're going to have to add 3. We're going to have to do this to all the points on our graph. We have 1, 2, 3, 4, 5. So what we can do is we can map them all out. So we have -3 and 0, -2 and 2, -1 and 0, 0 and -2, and 3, 0. So each one of these points is going to become a new point. So first, let's do the x-coordinate. So we multiply by -1 becomes a +3. Add 1, we get 4. 0 plus 3 is 3. Multiply by negative, so we get +2. Add 1 is 3. And 5. 1 plus 1 is 2. And 3. Negative times 0 is just still 0, so 1 and 1. That's going to be -3 plus 1, so -2 and 3. So now we can go ahead and take a look. We have our nice blank graph for us to draw. And they've provided the other graph just for reference. But we have all our points. We can go -2 and 3. We've got another point here at 1 and 1. We've got 2 and 3. We've got 3 and 5. We've got 4 and 3. Now, whichever order you plot them in, I was plotting them kind of up the graph or down the table, as long as we connect them in the order that we plotted them, we should be good. And if we look here, this looks sort of like this graph because it should look similar. We can see that it's been reflected horizontally, so these values across that y-axis have flipped. So you can see this little triangle part's over here now. It's been moved to the right, and it's also been moved up. Question 10. Bonnie was asked to determine the factors of p of x. Describe the error she made in her setup of synthetic. So again, we see that word describe. So we're going to need words. What did Bonnie do wrong? Well, if we notice here, there's a missing 0x cubed. And so there definitely should be a 0 right here. But we can't just do that. We have to describe what happened. So we could say Bonnie forgot to write the 0 for the x cubed term. Something like that. All right, question 11. Given the functions fx and gx, state the equation of f of g of x. Well, this is always fun. We have to do some function composition. So let's go ahead and go step by step. F of g of x means f of x minus 3, because that's g of x. And then everywhere we see an x, we're going to replace it with an x minus 3. So that's going to give us 1 over x minus 3 minus 1, which we could simplify as 1 over x minus 4. Let's go ahead and put that in the little blank provided. 1 over x minus 4. Now we also have to state the domain of this function. Well, the domain is going to be all the values that are good to go in our new equation. We can see that x cannot equal 4, but everything else would be good. So I'm going to write an interval notation. We've got another little blank down here for our answer. So we could put minus infinity to 4, union 4 to infinity. If you're writing it in set builder notation, you could write it as XER such that x cannot be 4. Question 12. Prove the identity. I always like these identity proofs. They're kind of fun. They're like a little puzzle we have to try to figure out. So on the left side, we have tan of 2x and we're thinking, well, maybe we're going to use one of the tan formulas. But on the right side, there's no 2 there. So, let's see what we can do. Well, we could write that cotan as cos over sine. And the tan we could write as sine over cos. This is the method of converting everything into cosines and sines. So maybe let's try that. So we have 2 over cos x over sine x minus sine x over cos x. And then because the left-hand side is simply just tan of 2x, we probably want to combine these different terms to make it a single term. So here we have to do common denominator. We're missing a sine x. Here we're missing a cos x. That's going to give us 2 all over cos squared x minus sine squared x all over sine x cos x. Now let's work on that left side a little bit. Tan of 2x we could write as sine 2x over cos 2x. And so both of these are actually going to have identities. Sine of 2x is 2 sine x cos x. And while cos does have 3 different options, I can actually see one of the options right over here. This looks like one of those cos 2x options. So let's use that one on the left side. This would be cos squared x minus sine squared x. Now the last step here is I have to do the division. If you think about this, this is 2 divided by this. So it's the same as writing 2 times, we can flip and multiply, sine x cos x over cos squared x minus sine squared x. And I guess one more step, 2 sine x cos x over cos squared x minus sine squared x. So left-hand side equals right-hand side, and we are done. Question 13. Given fx and gx, determine the equation of h of x, g of x minus f of x. Okay, so g of x is x squared minus 1. F of x is negative x squared plus 2. And we have to subtract these two functions. So this negative is going to go into both the x squared and the 2. X squared minus 1 plus x squared minus 2. So that's 2x squared minus 3. Let's go ahead and put that in the little section provided. So we have 2x squared minus 3. Now part B, we have to state the range of this function. Interesting. Well, we would have to identify what we're looking at. Usually the range would come from the sketch, from the actual graph. So I'm thinking this is going to be a parabola. Could I give it a rough sketch? I probably could. It looks like it's going to be moved down 3. It's opening up, so something like that. That's going to be the graph of 2x squared minus 3. So the range looks like y is greater than or equal to negative 3. Again, I'm a big fan of that interval notation. So this would be written as square bracket minus 3 because we include it, comma, infinity with a round bracket. 14. Given the graph of f of x, what do we have to do here? Well, part A, sketch the graph after a reflection over the line y equals x. Ooh, this is interesting. So this is that inverse transformation. We have to imagine drawing a line here. And then we're going to reflect all the points over this way, and these points reflect over this way. Another way to do it, if you're looking at just the points, is it's going to be a swap. So for example, the point over here, that's at negative 2 and 3, that's going to get swapped to 3, negative 2. And so it might be helpful to maybe do the swap with all the points. It might be helpful to kind of write them out. Let's at least grab those 3 points that we have listed there. So we have 1, 2, 3. We have minus 3 and 1, minus 2 and 3, minus 1 and 1. So it's going to become 1 minus 3 with the swap, 3 minus 2, 1 minus 1. Let's go ahead and plot those points on our graph over here. Got 1 point there, 1 point there, 1 point there. And then we can just continue on by noticing that the shape will look like this, include the arrows. We could grab those extra points if needed, but I think this would be sufficient. We can clearly see the graph here. And what's a restriction on the domain of f of x in order for its inverse to be a function? Well, clearly this new black graph is not a function because it fails the vertical line test. If I was to draw a vertical line here, it crosses at 2 locations. So to restrict the original function, I'd probably want to get rid of all this stuff, because if that was all gone, then I would just have the point at the top and then the point on the right. So I guess if I was going to keep this point here, that would mean keeping the point here. And then I would just have that top portion. And what that would do is eliminate this portion over here. Yeah, that would definitely be a function. That inverse would now be a function. And to do that, I would want to take values where x is greater than or equal to -2. So again, in interval notation, I could say the restriction would be -2 to infinity. That would be the restriction on the domain for f. Question 15. Describe a transformation of a function that would not affect its domain. Well, domain is going to be affected by horizontal transformations because those ones affect the x values. So we need to talk about a transformation that would affect the y values. And again, we've got that word describe. So let's write one. We could say a vertical translation of maybe 3 units up. Is that a transformation that would not affect the domain? Certainly. Or you could say any number of other options. You could say a translation down, you could say a vertical stretch, or even a vertical reflection. Those would all be correct answers. 16. Given the graph of fx, sketch the graph of y equals absolute value. Ooh, this one's interesting here. We're looking for a transformation we don't often do. This is going to apply because it's outside of the brackets. It applies to the y values. And we want to take those y values and make them absolute. So if they're positive, they stay the same. But if they're negative, we need to make them positive. So let's take a look here. We have the underlying graph given for reference, and that's really handy on this question. All the y values that are already positive, we can just dot them in right away. But here we have a y value that's negative, -2. So it's got to become absolute, pop up to +2. So on this section, the only one we have to change is that point. And then down here, we have to change this point. This is at -3. It's going to pop up to 1, 2, 3. Connect the dot, and we're good. 17. Determine algebraically all of the zeros of the polynomial function. Now, for determining the zeros, we have to look at that last term and the first term and those coefficients. So for the 12, we're going to look for factors of 12. That's going to be 1, 2, 3, 4, 6, and 12, and of course the plus minus. Then we're going to look for factors of 3, which are 1 and 3. Then we have to stack them up in that fraction, so you're going to have all the different combinations. So you have 1 over 1, 1 over 3. You're going to have 2 over 1, 2 over 3, 3 over 1, 3 over 3, 4 over 1, 4 over 3, 6 over 1, 6 over 3, 12 over 1, 12 over 3. Now some of these are actually going to simplify down. So for example, 12 over 3 equals 4. We've already got a 4 right here. So we can kind of cross that one out. It's an extra. 6 over 3 is going to be 2. We've already got a 2 over here. So we can cross this one off. 3 over 3, that's going to be 1. We've already got a 1 over here, so we can cross this one off. And of course, we have to put the plus minus in front of all these. So plus minus, plus minus, plus minus. So there's a lot of different factors we've got to try. But let's go ahead and try whole numbers because we're hoping that the people who made this exam were being kind to us. Which ones would be good to try? Well, I always start with the number 1, and then I'll try maybe a -1. I'll try a +2 and a -2, +3, -3. Those are good numbers to start with. So let's go ahead and start with 1. So we get 3. 1 times 3 is 3. 4 minus 16, -4. Yeah, that's not 0, so we got to back that up. That's not going to work for us. Let's try 2. 3, 6, 7, 14, -6, -12. Oh, look at that. We got a 0. So 2 is definitely going to work out. That's one of our zeros. X equals 2. Now we have to keep factoring, though. We have 3 and 7 and -6. And I'm just going to keep on trying with this. So I'm going to try maybe the 3. So we get 3. It's going to be 9. 16. Oh, that's going to be too big. Maybe let's try -3. So that's going to be -9. And -2, 6, 0. Oh, nice. So that's good. And this is going to give me my final version here. This is 3x minus 2. So I'd have from the 2, x minus 2, from the -3, x minus 3. And then I have this final 3x minus 2. And this is supposed to equal 0, so I want to write the final answers as zeros. So x equals 2. Sorry, let me keep it in the other color. X equals 2, x equals 3, and x equals 2/3. These are my 3 answers. And you can see that they were, of course, up here, right? Here was the 2/3. Here was the, oh, let's be careful here. I think I flipped the sign on the 3. This should be a +3. So it should be a -3 over here. So there's my -3 is over here. If this was plus minus. And then my 2 is over here as well. So they did show up in the list of possible factors, and these were the actual ones that worked out, or the actual zeros. If you didn't like the synthetic again and again, once you get down to this step, you could go ahead and write this as 3x squared plus 7x minus 6. And then you could use your regular factoring skills for a degree 2 polynomial, or even the quadratic if you wanted to as well. You only need to use synthetic to get down from degree 3 down to degree 2. Once you're in degree 2 world, you can use your old skills. But sometimes it's nice if you're doing synthetic to just see if you can keep going. All right, so that concludes booklet 1. Again, in booklet 1, there were some questions that required a calculator, and there were some questions where you might have benefited from one. But overall, you usually just need those calculator questions with your calculator, and the rest can be done without. In booklet 2, of course, there's no calculator usage at all. And we'll go ahead and pick that up in the next video. All right, I hope you enjoyed this video, and as always, thanks for watching.